Hi everybody. Welcome to the lesson on sampling distributions and some of their applications. This lesson is important to us because it's going to be the bridge between probability and statistics. Sampling distributions are at the root of all of the confidence intervals we're going to do and most of the hypothesis tests we're going to do. And that's going to be a lot of hypothesis tests. So I'll show you in the next couple of lessons that relationship. And I just want you to know from here on out that all of those statistical methods we do have sampling distributions at their root. This is an applied statistics class, so we won't do any more than this next couple of lessons on it. But if this were a theoretical statistics class, we'd be pretty much spending the whole semester showing how these sampling distributions are used to develop the hypothesis tests. Anyway, so let's start by talking about random variables. And I've referred to them before. I can't remember if I've actually defined this or not, but a random variable is a variable where the outcomes are subject to chance. Now, it doesn't mean they're completely random because they do follow a distribution. The ones we've been looking at follow mostly a normal distribution. And what that means is if I pick one at random, it's most likely in the middle. The farther out we get from the middle, the less likely it is. There are other distributions as well, but random variables, I just want you to know they follow a distribution. They have a mean and a standard deviation as well. Now, random variables describe the population. So if I'm talking about IQ scores, we're talking about how IQ scores are distributed for the entire population. So when we talk about picking one person, we mean picking somebody from the population. So that is to say that this mean here for the random variable is mu. It's the population mean, and the standard deviation is for the population as well, so it is sigma. So last time when we talked about the normal distribution, we were looking at the distribution of individuals. Those are random variables because if I pick a different person, I might get a different IQ score. Okay, those individuals had a mean. For IQs, we know it tends to be around 100, and those have a standard deviation about 15 for IQ scores. So now in this lesson, we're not going to look at distributions of individuals anymore. We're going to look at the distribution of a bunch of sample means. So X bar is a random variable because if I were to pick a different sample, I would be likely to get a different value of the sample mean. Okay, so just like the individuals, X bar has a sample mean. X bar has a population mean, and it has a standard deviation. And it has a distribution. The distribution of a statistic, or any quantity based on a sample, so the sample mean, the sample standard deviation, the sample proportion, you name it, has a distribution, and it's called a sampling distribution. And the sampling distribution is what this distribution is for X bar. All right, so the central limit theorem is important because it tells us what that distribution is for the sample mean. So a bit of notation. The mean of all of the X bars, this is read as mu sub x bar. So this is the mean of all of the possible sample means, or the mean of this distribution of sample means. Well, if you think about, if I were to take all of the possible sample means and find the mean of those, that's going to be the same as the population mean. So the distribution that I'm originally sampling from. So mu sub x bar, even though these are the same quantity, this one is referring to the distribution of all the sample means. This one is referring to all of the original population. So those values are the same, because you would expect the sample mean to hover right around the population mean. The same is not true of the standard deviation. The standard deviation of the sample means is less than the standard deviation of the original population. That's because if you think about taking a sample, or taking a whole bunch of sample means, every time you take a sample mean, you're basically picking the middle of that sample. So if you look at the distribution of a bunch of middles, that's not going to be as spread out as the original population. And it's less by a factor of the square root of the sample size. Now, here's where the central limit theorem is really, really useful. It's going to allow us to do a lot of stuff. The distribution of the sample means, according to the central limit theorem, is normal, meaning the sample means follow a normal distribution, provided we have a large sample, and I'll show you why a little bit later. Or if the original data followed a normal distribution. You only need one of those, but if you have both, that's even better. So let's look at our first example. And in this example, we're not going to find any probabilities just yet. Let's just see if we can determine that the sample mean follows a normal distribution. So let's take a sample of 15 small businesses, or at least we consider that we're going to, and we're looking at the number of employees. The question is, again, can we conclude that the sample mean follows a normal distribution? And we need to know that before we can find any probabilities relating to the sample mean. In this case, our sample size is small. It's only 15. And we're not told that we're sampling from a normal distribution. Therefore, no, we can't say that the sample mean follows a normal distribution. So we would need that information to proceed any further. So we can't go any further than that. Let's look at a second example. Suppose we know that the heights of mature oak trees follow a normal distribution with a mean of 80 feet and a standard deviation of 12 feet. The first thing that we're doing is we're finding the probability that one single randomly selected tree is greater than 85 feet. Well, if it's just one, that's not the probability related to x bar. That's just the probability of x. So this is what we did last time. And I put this in here because I wanted you to see the difference. So probability greater than 85. Like I said, this is exactly what we did before. So this is probability of z being greater than 85 minus the mean, which is 80, divided by the standard deviation, which is 12. My mouse pen is so slow, it's driving me crazy. So that's the probability that z is greater than 5 over 12, and I just use Excel for a calculator a lot of the time. So 5 over 12 is 0.42 if we round that to 2 decimal places. And if we go to our normal table, we can look up 0.42 and do 1 minus that value. So 0.42 is 0.6628. So that's going to be 1 minus 0.6628. Equals 0.3372. If you want to save yourself this subtraction, the probability that z is greater than 0.42 is the same as the probability that z is less than negative 0.42. So if you look up negative 0.42 on the table, you get 0.3372 also. All right. Next, does the sample mean tree height follow a normal distribution? Here, we don't have a large sample size, but they do tell us that the original distribution was normal. So the answer here is yes, because the original population was normal. Okay. Next, what is the mean of the sampling distribution? Well, that's mu sub x bar, which is the same as the population mean, which is 80. So mu sub x bar is mu, which is 80. And the standard deviation of the sampling distribution is sigma sub x bar, which we said was sigma over the square root of the sample size. And our standard deviation is 12. Our sample size is 25, so 12 over the square root of 25. So 12/5 is 2.4. All right. So finally, now what is the probability that the sample mean will be greater than 85? So here's what we're trying to get to. Probability that the sample mean, and I always suggest that when you're going through these, write the symbols out, kind of translate words into symbols. So probability is P of, the mean of the 25 is the sample mean, greater than 85. So now we need to talk about how do we convert from x bar to z. We know how to convert from x to z. We know that it's x minus mu over sigma. So this is x minus the mean of the x's divided by the standard deviation of the x's. Well, with x bar, it's the same thing, except we're going to subtract the mean of the x bars, and we're going to divide by the standard deviation of the x bars. Okay, so this is the same thing basically, except that now it's, you know, this is a parallel thing for x bars rather than x's. So this is going to be z greater than 85 minus, and we're subtracting mu sub x bar on both sides, so 80 over sigma sub x bar on both sides to get to the z is 2.4, and that is the probability that z is greater than, it's going to be 5 over 2.4. You don't have to use Excel for this. This is just how I do a calculator. So that's 2.08. And we know how to find this from the normal table. As I said a minute ago, the probability z is greater than a positive value is the same as the probability it's less than a negative. So I'm just going to go straight to finding the probability that z is less than negative 2.08. And you can verify that the other way. 0.0188. So anytime they're asking for the probability relating to an x bar, relating to a sample mean, you first need to verify that the sample mean follows a normal distribution. And again, the way you do that is you check whether the sample size is large and or you know it follows a normal distribution, or the original population, that is. If you do then verify that, you can find the probability using this formula. Convert to z and use the normal distribution. Okay? So just a little summary here. The population being sampled, so this is our original population, and then over here is our sampling distribution. The random variable was x because it represented individuals. It had a mean and a standard deviation of mu and sigma. The original population may follow a normal distribution or it may not. We are sampling n items from this distribution. If we happen to know that these x's followed a normal distribution, we convert it to z using x minus mu over sigma. For x bar, its random variable is called x bar, the sample mean. Its mean is mu sub x bar. Its standard deviation is sigma sub x bar. And we know that x bar follows a normal distribution as long as either one of those conditions is met. And if it does follow a normal distribution, and we want to find the probability, we convert to z, and let me see if I can make this a little bit bigger. Using z equals x bar minus mu sub x bar over sigma sub x bar, and we know that mu sub x bar is mu, and sigma sub x bar is sigma over the square root of n. So if you want to, you can go straight to this formula. All right, and if you want to see some more examples of that, I'd be happy to go over them in class. All right, so that's it for this lesson.